Okay, so in this video I'm going to talk about the software that makes my sonar system work. So when we get the data in from the water, the signals often look like this. Okay, so what I'm going to talk about in this video is the software that makes my sonar system work. So when we put our hydrophones in the water and we put a pinger out in the pool, we record our data and it often looks like this. And you get these deformations based on how close you are to walls and other things dealing with reflections and such. So we need to clean all of that up to make them look like this is the end result of the software that I've written. They turn into these beautiful sinusoids. So let's take an example of this second hydrophone here, this green one, and look at the steps that it takes to clean it up. So this is the before and the after for this hydrophone signal. And the first step is to run it through an FIR filter. We need to be able to get rid of these extreme notches, essentially. And we do that by running it through a running average filter, relatively simple, that does its job to smooth out those steps. Once that's completed, if you notice from this first figure, all of these signals have different amplitudes, and again that's through deconstruction and things of that nature. So we want to fix that in software, and I've written a normalization function that goes through and it looks at the peak-to-peak values, or the voltages of the waves, and multiplies that signal by a scalar based on what the peak-to-peak voltage is. Ultimately, we want to get it up to 4.096 volts, which is what the voltage should be when it comes in. Once that's completed, the next step is to interpolate the wave. Now, why do we need to do this? Ultimately, the goal is to calculate the time of arrival of these signals. If you notice, they all come in at different times, so you have these phase lags. Each one of these can give us a time stamp with respect to the first hydrophone, and that's what the whole goal of this is to collect those time stamps. So in order to do that, we need to have pretty good resolution, and you'll notice in this one we have 60 samples or recordings, and this was taken at about 500,000 samples per second. What we want to do is we want to get it up to about 2 million samples per second, which is what this is, you'll see here. It's the same number of periods, it just goes out to about 160 steps. So we do that using a piecewise interpolation function that I've written. So what we first do is we space out all the original samples and we fill them in with zeros, all the gaps in between. Then we run through and we take the next and the previous and take the average of the two, which will give us the middle value. And that allows us to upsample, or to interpolate into this nice function here. Once that's completed, you'll notice there's all these little squigglies in the wave. So to get rid of that, we run it through the FIR filter again, and out comes this beautiful sine wave. Once that's done, the next step is to actually run all of these waves through a cross-correlation function, which I can show you right here. This function, it slides two signals across each other, if you're familiar with cross-correlation, and it takes the sum of them, and what you do is you look for the peaks. Let me run this and I can show you. So when you slide two waves across, and you do the sum, multiply, shift function, there's going to be a peak that occurs in the resulting waveform, and that peak will tell you how much phase shift there is between the two signals, and that's very, very valuable for calculating the angle and declination of a signal source and how it comes in and hits your hydrophones. So I've written that, and you can see we have maximum values at these different locations, And there's 3 values because the 4th value is always 0. It's our reference point. Once this is completed, we can send the values out to the main computer, and it will run through it'll crunch the numbers and calculate the angle and declination.